Section 21.2, the force the magnetic field exerts on a charge. First, we want to recall when a charge is placed in an electric field, it experiences a force according to the equation. Force electric, really, is equal to the charge times the electric field. You know, if it's a positive charge, the force is in the same direction as the electric field. If it's a negative charge, the force will be in the opposite direction of the electric field. But that's about our only parameter, right, is the charge. And if it has charge, it will experience a force in the electric field. Turns out with the magnetic field, it's not quite so simple. A charge placed in a magnetic field only experiences a force if the following two conditions are met. So one, the charge needs to be moving. You can't just have a stationary charge. If the charge is stationary, it's not going to feel a magnetic force. The second one is that the velocity of the charge matters. So the velocity of the charge needs to be at least partially perpendicular to the direction of the magnetic field. Now that's depicted down below because that sounds a little confusing. In other words, the velocity can't be parallel to the magnetic field. If the velocity is in the same direction as the magnetic field, as is shown here, going to the right, or in the opposite direction as the magnetic field, going to the left, there's no force, at least due to the magnetic field. The only way we'll have a force is if instead the velocity is coming out at us, right? This is now at a 90-degree angle relative to the magnetic field. That's perpendicular, and that will produce the largest force possible when it's at that perfectly perpendicular 90-degree angle to the magnetic field. It's also possible that the velocity is somewhere in between perfectly perpendicular and along the magnetic field, right? It can come out at this in-between angle, but it still has a component that is perpendicular to the direction of the magnetic field. And you could show that that component is given by v sine of theta. So that's going to appear in our equation as well, because we most care about the velocity that is perpendicular to the magnetic field. And that's when we're going to get this magnetic force. But how do we figure out the direction of this force, right? The picture shows the force going up here, but that's not in the direction of the magnetic field or in the velocity of the charge. So where does that come from? Some of you might have an idea, maybe. If not, that's okay. We're about to cover it. The direction of the force can be shown with the right-hand rule. So for the right-hand rule, you're going to extend the fingers so that they point along the direction of the magnetic field, and the thumb points along the velocity of the charge. The palm then is going to give you the direction the magnetic force acts on a positive charge. The other way that you can do this is you can just do each of the fingers like shown, right? Where your index finger is the magnetic field, your thumb is the velocity, and your middle finger is the direction of the magnetic field at any given instant. Now this is true if it's a positive charge. If it's a negative charge, the direction of the force is going to be the opposite one, because once again, the negative charge experiences a force in the opposite direction as the positive charge. So you can either solve for it using the right-hand rule and know, oh, it's a negative charge, so the force is going to have to be down instead of up. Or the other way you can approach it, if you're feeling comfortable and confident with it, is you could use the left-hand rule, right? For the left-hand rule, you still have your finger is the magnetic field, your thumb is the velocity, but now your middle finger is the force. But this only works for negative charges, so be careful you don't accidentally use your left hand when you need to use your right-hand rule. That's a way we can get the direction of the force. How do we get the magnitude of the force? The magnitude of the force is actually going into the definition of the magnetic field. The magnetic field is defined as the magnetic force divided by the magnitude of the charge and divided by this component of the velocity that's perpendicular to the field, right? V times sine of theta, where the angle theta is between 0 and 180, and it's the angle between the velocity of the charge and the direction of the magnetic field. Previously, we just saw it in a picture. where we had magnetic field go into the right. And yes, that's one other factor. The magnetic field is the letter capital B. So that's an important note as well. So if B is going to the right, V is say coming down here, then the angle between them is that theta. And if you have an angle of 90 degrees, then you have sine of 90, which is just 1. And that's why you get the largest value of the magnetic field there. All right, now what about the SI unit of magnetic field? Well, if we want to get the SI unit, we can pay attention to the units of the components here, right? So the unit of force, SI unit of force is going to be our standard newtons. And then what about the SI unit of charge? Coulombs, yep. And the SI unit of velocity or speed, that is meters per second. Or the other way we can write this is because it's in the denominator as meters per second, we could then write it as newtons times seconds. The seconds could go all the way up to the top, per coulomb per meter. Now that's a pain to write that out all the time. So this is by definition equal to a unit known as the Tesla. Yes, long before electric vehicles were a thing, Tesla was a unit, right? So 1 Tesla is defined as 1 Newton times seconds per coulomb per meter, and it's abbreviated as a capital T. Another unit that sometimes pops up is a Gauss, and 1 Gauss is 10 to the minus 4 Tesla. That's a little bit more of a specialized thing, but that is an instance of that. Now that we've seen this, let's take a look at an example. How can we use these ideas? So example 1, magnetic forces on charged particles. A proton in a particle accelerator has a speed of 5 times 10 to the 6 meters per second. The proton encounters a magnetic field whose magnitude is 0.40 Tesla and whose direction makes an angle of 30 degrees with respect to the proton's velocity. See the figure. Find A, the magnitude and direction of the force on the proton, B, the acceleration of the proton. C, what would be the force and acceleration if the particle were an electron? All right, so as we look at this, what are some of the pieces of information given to us? We have this speed. Remember the symbol for speed is V. Great. We also have this 0.40 Tesla. That's going to be what? Our magnetic field. And then we also have the angle of 30 degrees, which will be our theta. Is there anything else that we know here? The other piece of information that's implicit is the idea of this proton. Since it's a proton, we know its charge is going to have to be the positive of an electron, right? Or positive 1.6 times 10 to the negative 19. Oops. Coulombs. There we go. So we're trying to find the force and the acceleration. What tools might help us out there? One is the equation we just got, right? We had it in terms of magnetic field, that B is equal to the force divided by the magnitude of the charge, divided by V sine of theta. And we notice that we know the angle, we know the speed, we know the charge, we know the magnetic field, so we can solve this for the force. How will we do that? We multiply the charge and V sine theta up to the other side. And this is often a common way of writing this, that the force is equal to the magnitude of Q times V times B times sine of theta, where theta is the angle between the velocity and the magnetic field. Once we have the force, how can we get the acceleration? This is where Newton's second law comes back in, right? We know that F is equal to ma. So we know the force on it. Do we know the mass? Once again, yes, right? Because it's a proton, we know the mass of the proton as well. 1.67 times 10 to the negative 27, I believe. But that's something you can look up. You don't have to know that off the top of your head. All right. And then what would change if it was an electron? It's an electron. We expect that the magnitude of the force would be the same, but the direction is going to be very different. Right? For when we have an electron, how will the direction change? The direction is going to need to flip. Anything else that will change? The other bit will be the acceleration, because the mass of the electron is also different. Because it's a much less massive particle, it should be a much larger acceleration if the force magnitude is the same. So that's sounding like a good theoretical overview for this. The other bit that we can figure out before we do any calculations is this direction of the force. So if we want to figure out the direction of the force, we can note, okay, if the magnetic field is going to the right, the velocity is coming out of the page, which I encourage you to try as well with the image, like, okay, velocity is coming back at me. What's the direction of the force? The force here is going to be up. Please try this out because you will need to be comfortable maneuvering your right hand to make this work. Let's look at the calculations now, see the end result. All right, so the magnitude of the force is Q naught, the charge, times V times sine of the angle. Plugging in all the numbers, we come out to 1.6 times 10 to the minus 13 newtons. Acceleration will be in the same direction as the force, and we can get with our F equals ma divided by the mass of the proton, and so it comes out to 9.6 times 10 to the 13 meters per second squared. That's a huge acceleration. For the electron, as we mentioned, the magnitude of the force is the same, but the direction is the opposite. And the acceleration, because the mass is so much smaller of the electron, the acceleration is 10,000 times bigger, at least 1,000 times bigger. That's amazing, right? Pretty wild to see. And we can get, again, that direction of the force will depend on the picture for how the magnetic field and the velocity we're drawing, the force would be up. So this gives us a much deeper, more rigorous understanding of magnetic forces and magnetic fields and how they work together. We'll talk a little bit more about how this perpendicular force will influence the motion of a charged particle when it's going through a magnetic field in the next video.